Good afternoon. My name is Michael Donovan. I'm the Global Research Director for CETCO. Today, I'll be presenting our research on ion exchange resistant GCLs for exposed liner and capping for mine closure. Geosynthetic clay liners, also known as GCLs, have been successfully used for many years in various aspects of mining and ore processing applications. These applications include heap leach pads, tailings impoundments, and caps enclosures. GCLs are typically used as part of an alternate composite lining system. This composite lining system is generally comprised of a protective cover soil, a drainage composite layer, a welded polyethylene liner, and a GCL. This system is installed over a prepared subgrade. Alternate composite liners have demonstrated much lower leakage rates than traditional compacted clay designs and can also be much more cost-effective. GCLs have also been used in a similar fashion for capping applications. Cover soil systems typically include a surface layer, a filter layer, and a drainage layer. Beneath these water management layers, a geomembrane is installed over the GCL to protect it from desiccation in the presence of calcium. I'll touch on why that's important in a few slides. The use of GCLs in capping systems is much more efficient because they're easier to install and require much less investment into cover soil placement. A typical geosynthetic clay liner design is shown in the upper right-hand side of the slide. These products contain either a granular or powdered sodium bentonite. The mass per unit area of the bentonite is generally somewhere between 2.5 and 5 kilograms per square meter. Typically, higher bentonite loadings result in lower hydraulic conductivities. The bentonite is held in the product through a needle punching process, where the cap nonwoven geotextile is driven into the base geotextile. The base geotextile can be a woven or non-woven material. As the sodium bentonite sees water, it hydrates and swells to form a contiguous gel. In freshwater applications, the bentonite can withstand many wet-dry cycles while still maintaining the gelling ability, which delivers a low hydraulic conductivity. So it's important when selecting a geosynthetic clay liner that particular attention is paid to the type of bentonite used. Generally, higher quality bentonites, which have higher montmorillonite content, higher cation exchange content, and generally have a low calcite content. In situations that involve higher electrolyte concentrations, the swelling potential of the bentonite can be significantly reduced, which can cause an increase in the hydraulic conductivity. You may wonder what factors influence the performance of geosynthetic clay liners. There are three water chemistry factors that can have a big influence on the performance of traditional sodium bentonite-based GCLs. The first is ionic strength. The ionic strength is related to the sum of the product of the concentration of the individual ions in solutions, such as sodium or calcium, and the overall charge of that ion. The presence of ions with higher valencies, such as calcium or magnesium, tend to increase the ionic strength. The next important factor is the ratio of monovalent to divalent ions, also called the RMD for short. The RMD is the sum of the concentrations of the monovalent ions, such as sodium, potassium, etc., to the square root of the sum of the concentrations of the multivalent ions, such as calcium, magnesium, and so on. The lower the RMD typically means the leachate is higher in calcium concentration. And the last factor is pH. At low pH, the montmorillonite platelets in the bentonite lose some of their negative electrostatic charge density, and electrostatic repulsion is therefore reduced. As the pH is increased, the higher electrolyte concentrations can have the same effect as typical salts in that they decrease the electrostatic repulsion of the bentonite. The combination of these factors can allow a practitioner to predict the performance of the GCL against a particular leachate. So how can you predict the relationship of the bentonite in a given leachate and its hydraulic conductivity in that leachate? Is there an easy test that can be performed to determine the chemical compatibility of the bentonite in that leachate? Yes, there is. So over the last 20 years, there has been a lot of research to determine how the performance of a geosynthetic clay liner is affected by the leachate chemistry. Craig Benson and co-workers developed a relationship between the swelling potential of the bentonite and the hydraulic conductivity of the GCL. In this particular study, the researchers investigated the influence of the cation type and concentration on the bentonite performance. They noticed that when the normalized swell values dropped below 20, the hydraulic conductivity showed a large increase. This free swell test was adopted as one of the ways to screen GCLs for chemical compatibility with a given leachate. Another area of research into the durability of GCLs was around the tendency of the bentonite to undergo an ion exchange reaction with calcium ions. The ion exchange of sodium bentonite occurs readily in the presence of calcium, as calcium bentonite is the most thermodynamically stable form. This study, also done by Benson and coworkers, examined the influence of dilute salt solutions on the hydraulic conductivity after repeated wet-dry cycles. The intent of the study was to determine the minimum RMD of a solution that would allow for repeated wet-dry cycles and still provide low hydraulic conductivity. The researchers found that below an RMD of 0.7, the hydraulic conductivity increased, with most of the effects of the exchange happening within the first few wet-dry cycles, and that was accelerated with higher ionic strengths. A subsequent study, also by the Benson group, was designed to investigate the relationship between the extent of hydration and the hydraulic performance of the GCLs after ion exchange. The researchers found that when the exhumed GCLs had water content greater than 50%, they maintained a low hydraulic conductivity even after ion exchange. To maintain a high water content in the GCLs, the researchers found that the subgrade water content must be above 10%. So in order to avoid the effects of ion exchange, traditional GCLs must be installed according to manufacturer's guidelines. The best performance is achieved when using assembly that helps avoid desiccation. The use of a geomembrane in combination with a cover soil layer, which is installed within 24 hours of placement, can minimize desiccation. So shown in the upper right-hand slide is an example in the field where they're covering the GCL with soil as it's being installed. If it's allowed to hydrate and then desiccate in the presence of calcium, cracks in the bentonite layer can be hard to see. So an example of that is the X-ray image shown on the bottom right. So in order to avoid this, it's best to also confine the bentonite in place, and that's confining pressure is generally provided by a cover soil. So for capping applications, we generally recommend the use of 1.5 to 2 meters of soil, and that soil should have a high water retaining capacity. For lining applications, it's required a greater than 15 kilopascals of stress be applied, which is equivalent to 0.75 to 1 meter of soil, which is less than the capping application. If soils that are rich in calcium cannot be avoided, for example, they're being transported from a far distance away, or anything else needs to be transported from large distances, and it's more cost effective to use the local cover soil. And if you cannot avoid calcium-rich clays, please contact the manufacturer for guidance. But even in the situations where you do have ion exchange, GCLs have been shown to be 98 to 99% effective after ion exchange if desiccation can be prevented. There are some situations where it is difficult to install a daily cover, and these situations are generally designs with very steep slopes. In order to help minimize desiccation, some engineering firms will use a light-colored textile to reflect the sunlight and reduce the temperatures of the lining system. However, sometimes this adds cost and can be challenging to install as well. So the intent of our work was to develop robust GCLs that don't require any special precautions to avoid desiccation. In addition, these products are designed to be used in a wide variety of cover soils that contain higher levels of calcium and be chemically resistant in the case of mining leachates and other leachates that are high in ionic strength. So our study focuses on the use of polymer-modified GCLs, or what is a polymer-modified GCL? Polymer-modified GCLs are products that contain a blend of bentonite and a water-soluble or water-soluble polymer. The polymers absorb water and fill the space between the bentonite grains and fiber bundles of the textiles. So depending on the polymer architecture, the polymers can actually anchor themselves onto the clay and help prevent the flow of water in the pore spaces of the clay. So the polymer chemistry can be tailored to perform in different environments such as caustic, neutral, acidic leachates related to mining and coal ash storage. For our studies, a series of 5 GCLs were produced with different polymer loadings. One of the important aspects of the quality control of polymer-modified GCLs is the analysis of the polymer content. We've been working with several universities to develop methods to better quantify the polymer content in the GCL. To measure the polymer content in the final product is a bit like unbaking a cake. The GCL samples are dried in an oven and cut into small squares. The squares are ripped open and the bentonite and polymer is extracted and milled into a powder to homogenize the clay in the polymer. Several tests can then be used to indirectly quantify the added polymer content, such as loss on ignition, fan viscosity, free swell, and fluid loss. Care must be taken when interpreting the results. We found it's best to have access to the base clay and base polymer in order to generate calibration curves so you know what the loss on ignition value, for example, means after you've done the test. And also, new research has indicated that if ion exchange occurs, this can also have an influence on the quantification results. The hydraulic conductivity of the GCL samples was measured using a flexible wall permeameter equipped with bladder accumulators. We followed ASTM method D6766 using falling head, rising tail procedure. The hydraulic gradient was approximately 150 with an effective stress of 34.5 kilopascals for standard testing. Testing that simulated higher effective stress was performed at 200 kilopascals. The effluent that we collected during the testing was analyzed for several different chemistry factors, including electrical conductivity, ion concentration, measured by ICP, and pH. The table on this slide shows the chemical composition of the leachates used for permeability testing. 7 different calcium chloride concentrations were used to tolerance the chemical resistance of the GCL samples. And finally, a synthetic copper leachate, shown in green, was developed to simulate exposure of the GCL under a heap leach pad. The chart in this slide shows the chemical resistance of each of the PMGs to the increasing calcium chloride concentrations. So each one of those lines represent a different polymer modified GCL formulation, with red being the lowest polymer modification and blue being the highest polymer modification, or black being the highest polymer modification. So the chart on the right-hand side of this slide indicates the maximum calcium chloride concentration for each one of the polymer modified GCLs to maintain a hydraulic conductivity below 5 times 10 to the minus 9 centimeters per second. The highest polymer modified, the most highly polymer modified GCLs allowed for a calcium chloride concentration of approximately 0.3 molar while still providing low hydraulic conductivity. These polymer modified GCLs were also tested for their durability against ion exchange in wet-dry cycling. In order to do this test, PMG samples were cut into 8-inch by 8-inch squares. The edges of the squares were sealed using a caulk, and this would help prevent the polymer and clay from leaving the sample. To protect the samples and allow for maximum water exposure, the samples were sandwiched in between 2 drain boards, and rubber bands were used to keep all the materials together. The samples were allowed to hydrate for 48 hours in mild calcium chloride, sodium chloride leachate solutions, which had an RMD of 0.007, so very low, and an ionic strength of 0.025. The samples were hydrated for after 2 days and then taken from the bath and allowed to desiccate for 7 days. Several tests were used to monitor the extent of ion exchange. The first was monitoring the bath water, where we measured the ratio of calcium to sodium. For most samples, a plateau was reached after about 15 wet-dry cycles. Another test that we used to monitor for ion exchange was the amount of water absorption that each of the samples had after a wet-dry cycle. Most of the samples actually showed a fairly steady mass uptake over multiple cycles, which highlights the chemical resistance of the polymer clay blend. Even as the product is going through ion exchange, it still maintains its high water absorption capacity. which is one of the reasons why these GCLs work so well. The most highly loaded polymer GCLs generally allowed for the highest uptake, which is the light blue squares. This chart shows the influence of ion exchange on the free swell of the samples. The free swell of the samples decreases as the samples undergo repeated wet-dry cycles. PMGs with higher polymer loadings maintain the highest free swell values even after 20 wet-dry cycles. This chart shows the relationship between the hydraulic conductivity of the polymer-modified GCL and the free swell after ion exchange. The hydraulic conductivity tests in this example were done in a 0.01 molar calcium chloride sodium chloride solution. Even after ion exchange takes place, the hydraulic conductivity only increases by approximately 1 order of magnitude. Despite having a free swell of less than 13, the sample still showed, in some instances, the sample still showed relatively low hydraulic conductivity. This chart was developed to compare the hydraulic performance of the various PMG samples to standard sodium bentonite-based GCLs. The highest polymer loading is represented by the bar on the far right. The purple bars basically show the performance against deionized water, with traditional bentonite-based GCL performance, the bar on the furthest left. You can see that they have similar hydraulic conductivities in the range of 1 × 10⁻⁹ centimeters per second. The green bars show the performance against 0.01 molar calcium chloride prior to any ion exchange processes that have taken place. So this is just fresh polymer modified GCLs tested against 0.01 molar calcium chloride. You can see that for traditional bentonite-based GCLs, you saw a slight increase in hydraulic conductivity. And also, interestingly, we saw a decrease in the hydraulic conductivity for the polymer modified GCLs. The blue bars show the hydraulic performance after exposure to multiple wet-dry cycles during the ion exchange experiments. Traditional GCL samples show the largest increase in hydraulic conductivity after only 4 wet-dry cycles. You see an approximately 4 order of magnitude increase in the hydraulic conductivities. However, our new polymer modified GCL samples demonstrate only a moderate increase in hydraulic conductivity to this calcium chloride solution after ion exchange. Our new polymer modified samples actually can be more chemically resistant to copper leachate. So what we did for the next series of experiments is we took the same samples that are being tested against the 0.01 molar calcium chloride solution, increased the effective stress to 200 kilopascals, and introduced a copper mining leachate. The PMG samples show a much lower hydraulic conductivity in the synthetic copper leachate, with performances less than 1 × 10⁻⁹ centimeters per second, even after complete ion exchange. Whereas the traditional bentonite-based GCLs show no improvement in hydraulic performance after ion exchange and even after the effective stress is increased. So in conclusion, these new polymer modified GCLs show good chemical resistance to leachates. The polymer clay blends have improved swelling and sealing capabilities, and the materials are economical and have much more robust performance after ion exchange compared to traditional GCLs. The product can perform well against aggressive leachates even after ion exchange, and higher polymer loadings give improved chemical resistance. Higher effective stress results in lower hydraulic conductivities, and the new product should allow engineers to design more cost-effective installations that have greater installation flexibility. So on behalf of CETCO and my co-authors Barbara Gebka and Denny Wind, I'd like to thank you for your attention. I'd also like to thank the organizers for allowing me the opportunities to speak with you today. And if you have any questions, please contact me through my email. And please be safe and enjoy the rest of the virtual conference.